So yeah, welcome to my talk. This time the talk will be something like a different perspective for me because I'm usually a developer, but today I take the role as an AI engineer, and I will show you like some stuff that I did like in the past. And from my perspective, I'm a bit primed into one direction because that's for me like the perfect solution for the problems that I solve with machine learning. So I tend to rage and have a strong opinion on other concepts, but I'm trying to give you like a clue on what kind of technology you can use for what kind of problems. And I try to explain that with as easy problems as possible so that you can figure out what the problem is and how to describe it yourself. So yeah, let's get started. So this is something like an adaptive neural network guide, in short ANN, but I'll explain it later what it means. First, the overview. So, from a developer perspective, what does machine learning actually mean, or what does deep learning mean? Or what are the different architectures of neural networks, and why adaptive neural networks are so awesome? So, let's hard to plan from my engineering perspective. So, machine learning is hard to describe. Currently, it's something like a total buzzword for pretty much everything related to data, and that kind of sucks because it's hard to gain knowledge then. Basically, it's something like teaching a machine to do things itself, or teaching a machine to describe problems itself. The description part is really harsh and really problematic right now. And finally, teaching a machine to solve problems itself. That's basically the basic idea of machine learning. What should it do? So given we have a problem, we use machine learning as a technology to solve a problem or come up with a solution. What it means in particular is something like we have something like a data set, no matter how described or no matter what kind of data we have. We have a classification and a yes and no to a question. But the question currently we as humans have still to write. So we have to define our question and how to measure the question or the answers for that. And more specifically, currently it's like that we have a data set and we do an analysis of the data set and try to come up with a yes and no to the same question. And that's the analysis part of over the time series is the idea of prediction. But that will be explained later. The basic training idea is that we have something like a dumb neural network. We do some training, some fancy training, and we come up with a solution for that. And it figures the solution itself out. We have a clever neural network afterwards, and then we test it. And then we have a yes and no to a question that we have asked before. Important part in the neural network world is that you have a specific training data set and a test data set, and you don't combine them. Because if you combine the data set with the training data set, the solution will always be true, and that's not what you want. You always want a probability. And if you test, if I ask you like 500 times the same question, like, are you clever, all the time, and you always reply with yes, then you know what I'm going to ask before giving the answer, right? So the idea behind training data versus test data is to prevent the machine from knowing the answer already and to figure it out itself. That's why you split up training data and test data. So this is like only the basic stuff. There are different kind of architectures in the machine learning sector. There are different subsectors where they actually came from, and maybe there's some it's weird to sort into different categories, but I would describe them like having a math sector, a biology-inspired sector, and an engineering sector. The math sector is like low-level neural network stuff, and the evolutionary neural network stuff is something like in between the math sector and the biology sector. The recurrent neural networks that Patrick was introducing before, Q-reinforced recurrent neural networks, which is the QRNN stuff. Convolutional neural networks that are not covered in this talk because it would blow up everything. And that's basically the math sector, or the idea behind how to solve the problems and coming up with like a functional definition of the problem. The biology sector is currently mixed between the evolutionary idea and the HTM engine. The HTM engine is something like hierarchical temporal memory engine. And that means it's completely different from everything else you know, I promise you that. And it's completely mind-blowing what these guys already achieved. And it's something like a really, really new concept, and they can automate very, very, very cool things with that. Like teaching a robot how to walk and stuff like that. with no computing power. But it's also covered here because HEM is completely different from everything else. Just that you know it, HEM is awesome, and I know some of the developers and they really know their shit. From the engineering sector, there's something like the adaptive neural network stuff, or currently they are more described as artificial neural networks, but as everything here is artificial, artificial neural network developers try to describe them as adaptive neural networks because that's what they are adaptive to the stuff. There's the need concept, the hyperneed concept, and the ES hyperneed concept that I will explain in the very last, because that's basically what I do for a living, and I'm trying to give you first some hints on and clues what the other solutions are and what they can be used for. So what specific kind of problems they are able to solve with these. So, architectures. So I think I'm quite sure I'm in between the biology and engineering sector. So when I do something like, when I do a statement, I'm not always sure. I, as a human, okay, now a fun fact. Every human is completely different by 100% after 7 years of his life. Every single cell in your whole human body is completely replaced after 7 years. So that means every knowledge that you have, and when you come up with a solution, is not the whole lifespan that you have, it's only the past 7 years or the past 14 years if you remember it all the time. So that's basically when you do a statement and you come up with an answer to a problem, you always have a limitation in a time span. And that's a really harsh problem because we cannot access all our data that we have learned before in our past. So that's why I say I'm around 0.65, like 65% sure that I'm actually somewhere in between the biology and engineering sector, because I can't say it for real. So now we can start with like the basic neural network stuff. What is the idea behind them and what they actually do? Neural networks is basically the idea to build a human brain. That's the basic idea. We're not quite there yet. Neural networks can figure things out on their own in a limited way. They have something like a basic treatment, like a reward function, like good dog, you did everything good. If it was identifying things correctly, and a punishment method like bad dog, and you punish the dog, no, it's bad, don't poop on the floor. Then it's basically the opposite around. So you train a neural network in order to let itself figure out what was right and what was wrong. A neural network is basically like this. So that means we have some kind of input sensors, not described right now what they actually are because we go into that in more detail later. We have like the input sensors on the left side, we have something like the hidden layers in between, and the output. And that output can be the basic setup like a yes or no, or a probability with like one output, and we have like a probability of being 50% in one direction, 50% in the other direction. And that's basically what all this neural network stuff is. You come from the left and go to the right, from the input to the output side. In like the 1980s, there was like a huge thing which like revolutionized the first AI summer, because we're in the second AI summer right now, or the third, depends on your views. And the idea behind backpropagation was that neural networks will get better over time by rewards. So that means if I say good dog, yes, you did that right, then the dog remembers that, oh, I get a treatment every time I do not poop on the floor. So that means I just don't poop on the floor and I get always a reward. So the basic idea behind neural networks is that they should get better over time by rewards. So if you say, yes, you did it good, then it should modify itself in order to get better. And that's what modifies it is the backpropagation algorithm. How the backpropagation algorithm works is not that quite important. There are very, very mathematical papers about it, and they suck hard to read because it's totally dumb to use math for that. Basically what it is nothing more than having two different arrays. One is the arrays of the left side of the hidden layer, and one is the current one that you're iterating through. And based on a so-called training function, I'm explaining that later, what it is. Based on the training function and the thing that it returns, you update the layer that you were iterating in the outer loop. So you have something like for var e in, for var a in the first layer, do this. For var a in the second layer, do this. And if you have this as a second layer, and you figure out that this value, I'll describe it later what it is, but if you get a value like in a specific way over 0 to 5 back, then you say, okay, we got a better result here, and it was okay based on the training function. So that means we need to update the connection before. So like this one or this one based on how they connected, but that's not important for now. So basically, it's something like caching two arrays, iterating over each array, and then updating the outer one. That's all about backpropagation. That means the outer array is the previous set of neurons, the inner array is the current set of neurons in this hidden layer. If the training function returns a value bigger than 0.5, for example, then we update the previous neuron with the new value that comes back from the training function. Training function is currently not important, just everything step by step. Neural networks are built that way that they can only work with vectors. And vectors in the sense that they have something like floating point value, which means they are just determining from 0 to 1. Because it's easier to implement and we have computers that can decide between 0 and 1. Basically that's it. Why. And the idea is to have like each neuron that was inside this grid has a value from 0 to 1. 0 means no, 1 means yes. And it means something like a probability of yes. So if it's like something like 0.9, then it means it's like 90% sure that it's a yes. Neural networks or neurons themselves don't question treatments or punishment, so they don't kind of ask them questions. So why did I do that wrong? You weren't supposed to punish me because I didn't poop on the floor. So basically, they don't question their treatment or punishment, and that's the harsh problem and the manual part that people should do with supervised learning, but I'm digging into that later. They don't question their data sets, so they don't question if that was actually a fraud that he wasn't supposed to poop on, or if it was okay to poop on the terrace out there or so. They don't question the input vectors, so they don't question if that thing that they were supposed to be analyzing is actually correct or not. And they don't question the output vectors. So that's basically the base problems of neural networks. An example of neural networks is, and networks usage is, given you have a data set with like millions of cars and you have always like a simple data set, totally simple, having a good car with 4 wheels and having a broken car with only 3 wheels. And that means we have a neural network that has 4 inputs. 1, 2, 3, 4. 1, 2, 3, 4. And it should return yes, it's a good car. When we have like 4 wheels, it should say no, it's a bad car when it's having only 3 inputs. So that means we have on the left side, back into our neural network idea, we have like 4 inputs. On the right side we have yes and no. And only with the broken cars it should reply with no. That's the basic idea, to analyze how many cars were broken and were still driving, and how many cars were good and were driving as well. The problems, so that this problem is a so-called classification problem. That means you train a neural network to classify a different data set in order to figure out what it actually was, or what the or in order how to answer the question. That means a data set in this case has like 4. It has like 1 vector with 4 different entries and 4 wheels as inputs. That is a mistake. So that means a vector itself could look like an array of like 1, 1, 0, 1 in our broken car case, or whatever kind of data representation you want. A neural network needs treatment if it found a broken car, assuming that broken cars occur less than working cars. If you have like more, broken cars if you have like more broken cars than working cars, then it would be the other way around. So you only treat the case that it was good and well identified if it is occurring less in the data set, because it doesn't make a difference if you treat it only like 10% of the time and it figures out, well, why the fuck should I still do that? I can always reply yes and I still get enough rewards. Neural networks can also be seen as dumb monkeys that only want their banana. They literally do everything to get their fucking banana. That's actually what they do all the time. They're really, really dumb, they're not smart, and they only want their banana. That means they also don't question their reward. At least if they get a banana, everything is good. They don't have a sense of time by default. I'm digging into that later. They only know good and bad, and no matter how long the time spent. So that means if they have no sense of time, they can't see if like the next 10 cars will be not broken again, or if like the first 10 cars were broken and it was just a coincidence that the first cars were all broken. That's a so-called overfitting problem, like a depressional behavior or an optimistic behavior. Imagine a dog that gets like treated all the time, gets like yummies all the time, and will be an annoying piece of shit because it will bell all the time and like poop everywhere because he thinks he can do everything, if you treat it always. If you punish it always, then it will be a depressive behavior, so that means it gets frightened of you. The same kind of behavior can be applied to neural networks, because if you treat it always good, it can't figure out what went wrong or what is the wrong case. And that's a so-called overfitting problem. So that means if we have like the first 1,000 cars that are good, then it basically assumes, okay, we have like 1,000 good cars, so why the hell should I analyze bad cars in the first place if everything is good as well? But if like the next 1,000 cars are then broken, then it means it will still reply for like 500 times of the next 1,000 cars. No, they're still good. I can't see what's wrong with that because it can't identify the things. That's a so-called overfitting problem. And that's basically the harsh problem behind that. How to treat and how to punish neural networks. That's a real discussion, whatever research is done, being like in 5 million sectors that you can imagine, but it's the basic problem. A problem with classification is also, it's a so-called labeling problem, when you have like a good car with like 4 wheels, and then suddenly you have something like a truck in a data set, like 6 wheels or so. And then the neural network will assume, okay, has 4 wheels, so that means it's good, right? Because I can't value like the other 2 wheels, but it still has 4 wheels, so everything's good, right? That means datasets cannot be used or assumed to be finite anymore. Finite datasets means they are complete in their vector size, which is like the size of 6 here in this array. And when we assume like that we have like 5,000 or any kind of big number cars that have 4 wheels and only like 10 cars that have 6-wheel cars, those 10 cars are really close to always identified incorrectly, because the neural network cannot make sense of the additional 2 wheels. There's a so-called labeling approach of labeling those different kind of cars, like as a truck or as a car, so that they get treated differently, but that's an optimization that I will not dig into. Basically that means if you have like 6 ones here for 6 good tires, it will assume that it's a good car. But if in our case we have like the last 2 are broken or so on our truck, then it will always come up with a solution that it's also a good car, because the last vectors are not making any sense in the other purposes, so they're still good, right? That's basically the problem behind that. So the problem with such changing data sets is how can we adapt to like such classifications? How can we adapt to new dataset vectors, or if the vectors in size change? And how can we adapt to minimally occurring marginal conditions? In that case, our trucks that we have like only tens measured, and if we have like only tens of like trucks, it's really close to impossible with that kind of technology to figure it out. But humanity is clever, so they came up with a solution. Back then, in the first AI summer, when everybody thought Skynet would evolve and would come up with like destroying humanity and stuff like that, we had the idea that we use evolutionary cycles and the idea of evolution in order to come up with a better solution. That was the first AI summer. Back then we had the problem that our technology was crap because nobody had a computer at home. Meanwhile, we have like, I think, 1.7 million-fold better computers than before 30 years, so we are really close to getting the AI stuff ready. Evolutionary cycles work pretty basic. They have the idea of classifying the dominance of one specific agent. One specific agent means that we have a system of like hundreds of different agents or hundreds of different neural networks competing against each other and trying all to figure out a solution. And the ones that are stronger get more dominance, so that means they are more important in our gene pool and they get to mate each other. So that means they can produce babies with other good fellas, and the lowest ones that have like no fucking clue what's going on, they just get sorted out and get killed. The genome or DNA representation is from the DNA standpoint is the weights of the neurons. So if we have like a neural network from the left to the right, again with like our array, each single bit or value of that is basically one cell in the or one DNA part, and altogether are basically the DNA. That's super simple to implement, like one giant array of like array map and one array and stuff like that. But yeah. So that means we have a neural network, no matter how it's primed, with like 1s and 0s and 0 and 5s in it, and we have our genome. And each one of those parts represent like one neuron at a time, and stuff like that. Super simple to implement. Only problem back then was that we didn't have enough computing power for that. The idea behind evolution cycles is also to split the genome DNA. So that means we have two babies that are produced, a son and a daughter, and each of those have one more dominant gene part of one side. So that means our daughter basically looks like the mother, and our son looks like the father. That's the idea. So what it looks like is that we have our DNA split. Like if our DNA split would be like at 80%, then it would be here at 20%. So like vice versa. And we use those parts to create our daughter, and we use those two parts to create our son. That's basically the whole idea. And if we use that methodology, we have the idea to, as these two are the dominant, or can be assumed to be a dominant gene, and as these two parts are randomized, randomization will always come up with the perfect solution for the current time. Because if we have like a system that is always like combining always only the dominant parts, and if given enough time, like in the sense of like 1,000 years, somehow in 1,000 years there will be a time where the randomization of this part will come up with the perfect solution for the task, like the perfect solution that is not optimizable. That's the idea, that randomization will come up with a solution. That means evolution will always win, randomization will always win, but only given enough time. And enough time is the only thing that we don't have, so that kind of sucks. That's basically why it failed in the first answer. The disadvantage?
No classical padding anymore?
Huh?
No classical good dog padding then, in that case?
No. Those are all treated, but the idea behind evolutionary neural network is that you don't have only one neural network, you have competing neural networks. Like thousands.
Treated as well.
Yeah, 1,000 dogs that are treated, and everyone that is like the best dog, like the best not pooping dog, this one will be like getting to mate with the second best dog, for example. And as they are all like neutral in their sex, they of course can mate each other. But yeah, we don't decide between sex and racism and stuff like that. The disadvantages of neural networks of evolution cycles is that they are adaptive to bad seasons and that they are adaptive to good seasons. So that means if they figure out everything is wrong, everybody in the whole gene pool will come up with the wrong solution, and they get depressive. If they come up with like the optimistic stuff, then everything thinks it's good and everyone's happy and live in total communism or so. That means evolutionary cycles need a long time to get better, and they need parallelization of hundreds of agents. Back then, like 30 years ago, we had like a supercomputer with 100 megahertz. And we can imagine that this kind of shit is like really hard to compute for that. So people came up with a better solution. They first wanted to figure out what the advantages is. The advantages of evolutionary cycles are that they will of course always come up with a correct classifier or correct solution. They are adaptive to infinite datasets and they are adaptive to time-based datasets, but they need more time to compute. But as I said, that sucked because like nobody had computing power for that, so they came up with a better solution. The better solution for that was back then going back into more detail into the backpropagation algorithm, like the thing that rewards our neurons. Backpropagation, just as a reminder, was the outer last hidden layer update function. So like the two arrays, and we update the left side. The typical behavior of a backpropagation is that we have a sigmoid or a Gaussian behavior. That's basically the idea. Depending on the use case, we can use sigmoid or Gaussian methods in order to prime those neurons. And basically what that means is we have something like a sequence update function, and it means if our value, for example, is here 0.5, and we get like an input of 0.7, then we are getting close to here. And the idea behind the sigmoid curve is that given we are over this mark in the direct middle of the chart, then we have a fast learning curve. So that means it learns faster, but has slow overfitting because the curve flattens out. And if it flattens out, that means it will figure out, okay, yeah, maybe the last 90% of cars were all broken, but I'm not quite sure yet. That's basically the idea, to have something like a slow forgetting curve. But that will always fail because we are now more clever than that, but that was basically the idea. When we use a Gaussian update function, that means if we are at 0.5 and we have like a total update value of like, if we are at 0.5 and we update everything close to the 1.0 value, then we have a fast forget curve. Gaussian curves start here and end here, and they make both, no matter how you have them, but that's basically the idea behind Gaussian curves. And what it means is that we have like a fast learning curve on the left side and fast forget curve on the other side. So they are really good at forgetting stuff that you learned before. What it means is nothing more than if the function result of that specific function or implementation that is always like customized, and if the value is bigger than 0.5, then we increase the neuron value from the neuron that we memorized from the before hidden layer. If the result is lower than 0.5, then we decrease that neuron's value. It's basically the whole story. The problem with the backpropagation stuff is, or with, given in the sense that we're currently only in neural networks, if we have, for example, a broken car with like 3 tires, and one tire has like 0.3 of air pressure, given like 30% air pressure, and when we have another car that has also a flat tire, but given only 0.7 like as an air pressure, or 70% air pressure, then this will be classified as a good car, and this will be classified as a broken car, because 0.7 is closer to the 1 value than to 0, right? So that means, on the other hand, if we have like given our truck a car problem, and we have like our car that is broken with a flat tire and 0.3, then it will be classified as a broken car. But if we have like our truck with 2 broken tires, and one is like 0.3 and one is like 0.7, it will still be a good car because we have all those 4 tires, and given it respects like 5 tires, it would classify those as working. Yeah, and if the value here would be 0.75, it would still classify both tires probably as good. And you need like exponentially more wrong cases in order to prime that back to like not identifying that as good. So the problems with the backpropagation idea, or problems that we have in the behavior and how they learn or forget, is that the input vectors influence the reward function, so that we figured that out already, because from left to right, and we update everything. And we have a so-called time and occurrence problem. So that means if we have like, again, like those 10 trucks, we still have the problem that we can't figure out what we should do with those 10 fucking broken trucks. And we have a time problem. So that means we will forget probably in future if we have like 5 million cars that work and one that doesn't work, we tend to ignore it because we think, no, that was like will never happen again anyways. And again, we have the problem with like 6 wheels occur less than 4 wheels, but 6 wheels, no matter how broken they are still like a 4-wheeled car if 4 wheels were working correctly. And there's a new reward function necessary for a bigger set of inputs. So that means if we have like to respect not only 4 tires and we have to respect like 6 tires, we have to write ourselves as humans that program the AI or program the neural network. We need to write a new function that respects all those 6 tires and not only the 4. And the question is now how to value different rewards for different inputs. But there's of course a solution that people came up with. I think it was like in the 90s or so. It is called recurrent neural networks. Recurrent because it will reoccur somehow. But recurrent networks are so-called unfolding neural networks. That means, given new data sets and given new iterations over each data set, like over each car that we have in our 1,000 cars array, we each create a new step inside the layer that will unfold itself over time, so that it can remember what kind of car was broken before and what kind of car will probably be broken in future. That's the idea behind the whole story. That means we have a hidden layer that creates another dimension, and the unfolding term leads to the sense of time or occurrence. So that means if we figure out that 1,000 cars were broken and 10 cars are not broken anymore, then we can easier switch to like after 3 cars or so, then it will figure out, okay, probably next car will still be broken, because you can memorize the last 2 steps and figure out, okay, now it tends to be broken, everything, shit is on fire, so I need to figure it out already. What it means is, typically we have something like a neural network that looks like this, with a static set of input of hidden layers and a static set of neurons per hidden layer. And now with the recurrent neural network we have so-called time steps. So that means this is basically representing the t-1 step, the current time step, and the t+1 step, the future time step. The disadvantages of recurrent neural networks is that it's super ineffective, like literally, and the computation time gets longer with more data sets. Because we remember each part of each different data set with our new hidden layer over time. That means if we are like in the step from 1 to 2, we have like 0 computation time, but in the step from 999 to 1000, we have like literally 1000 times over 999 minus 1 computation steps to do, and that's like a shitload of computation time, of course. That's basically the reason why this is all optimized by now on GPUs, because GPUs are pretty good at parallelization stuff. Also, we have the problem that each change in dataset vectors need manual correction of the reward function. Still a problem, still not solved. Eventually, RNNs, from my personal subjective view, will always lead to hacking the reward function. So that means the idea behind recurrent neural networks is, if they remember everything correctly, they will get pretty efficient at detecting stuff, but they will also get pretty efficient to do the stuff that you would expect them to do. So if you have like a reward function that is made for like cars and for both cars and trucks, it will eventually decide, oh, if it's 6 input vector, and if those 2 tires are broken, then it basically wants me to say no, so I say no. So mostly RNNs will be coming up with a single Uber strategy that is not modifiable, so they figure out like, okay, this is the way to go, this is the way to solve it, and they come up with a Uber solution. And the idea behind Google, that's what Google DeepMinds was doing and stuff like that, is basically this kind of stuff. It's totally super easy, but yeah. The advantages, however, of recurrent neural networks was, again, that they can understand labeled data, because you can figure out, okay, I memorized this was a truck, I memorized this was a car, so I can predict more easily if more cars are broken right now or in future. And they're very good at generation stuff, which is something like, due to the backpropagation behavior, those are the kind of neural networks that you use in order to have like a data set of all your handwriting in your book or so, and then they can generate like your own writing style based on the stuff that they figure out how you write an E or a T or any other kind of letter. So they're very good at generation stuff, and that's basically their purpose. And they can generate what you think a cat is. So that means if they figure out like 5 million cats look like always the same, they always have a tail, they always have like the same shape of their head, then it can generate, or the idea is that they can also generate like what they think a cat is. Basically pixel stuff is totally complicated because all of the filtering stuff, but I'm not digging into that more. But that's basically their strength and why they are used right now. But as we figured out, one of the disadvantages of RNNs is that they tend to be overprimed and come up with a single Uber strategy, and that's not what we actually want. We want them to forget. There's a so-called LSTM RNN, which is a long short-term memory RNN. Basically what it does is that it can forget data and forget training that was irrelevant. So basically if you trained it like 1,000 cars and it figures out the last 200 cars had all 4 tires were off full, it figures out, well, I knew that already, I can't forget it, I don't fucking care, and then it will just don't remember it in its unfolding over time. And it introduces new hidden layers per hidden layer, which are so-called forget gates. I promise you this is like the most complicated chart that I have in there. I promise you, really, that's like the most complicated chart. I couldn't describe it more easily. But given the idea that we have like our RNN that has unfolding layers over time, so this was like our first card, second card, third card with the 4 layers. Then we have for each hidden layer in there, we have like a new layer that computes everything, which is connected. This one's connected to this, and stuff like that. Like all 4 are connected. And then we have different filtering functions. And those filtering functions are somehow voodoo mathematical stuff. People prove that this is the right way to do it, so it doesn't matter. What it does is basically, if you run a sigmoid and a tangents, the negative tangents on it, then it will come up with a maybe, and if that is combined with those, then it's definitely a yes, and if it's combined with like the sigmoid function, then it's no, and you can forget it. What it does is nothing more than using this value, and if it's like 0.51 or something close to 0.5, then it runs all those functions through, and if this value is like lower than 0.5 and this one is lower than 0.5, then this will always be lower than 0.5 and it can be forgotten. But if this is like bigger than 0.5, and this one was bigger than 0.5 as well, that means, okay, we remember it. That's basically what those kind of stupid, totally complicated functions do, and these are the so-called forget gates. Totally complicated. I think they were easy to explain. It's just mathematical stuff. You can do it on your calculator if you want to, but that doesn't matter because there are libraries for that. The idea behind those so-called forget gates is that the values close to 0 or close to 0 difference from the previous priming or the previous value of the neuron are ignored and forgotten. So that means they are very, very good at identifying positive values. So if they figure out, okay, we have like 10 trucks and only those 10 trucks matter because I'm a fucking truck detection algorithm, then they are really good at identifying those 10 trucks. But they are very bad at identifying negative values. Like, what the fuck, this is the plane, I can't recognize it, and they will totally ignore it basically. Because that's kind of a labeling problem, but that's different, and I'm not digging into that later. The disadvantages of LSTM RNNs is basically that they are very good at reoccurring datasets. So if like 1,000 cars reoccur every time, they can remember them, and they are very good at it because they can also compute it faster because of those forget gates. They figure out, okay, I know how 100 good cars look like. Basically, the next 900 cars will always look the same, so I can decide, okay, I now know how cars look like, and I can forget like all the other stuff because they always look identically. And I don't need to remember the color or stuff like that. And basically that's something like the computer implementation of Captain Obvious. It will always make like the most obvious statements that you can imagine, and it's very good. But it's also bad at identifying new strategies. So if you have like a different kind of data set, different kind of label data set, they are really bad at identifying them or adapting to the new problem. So that means there's a new strategy required that combine those multiple RNNs in a line or a graph. And that's, for me, that is the definition of deep learning. For me, as an engineer that is not familiar with all the buzz bullshit, because I started like 15 years ago with that stuff, is deep learning is for me the combination of neural networks. So if we have like one neural network that gives out a maybe and another one that gives a yes, then the combination of those will give a yes. If we're at 0.5 and bigger than 0.5, then that will be a better probability. So for me, deep learning is something like a probability algorithm and a combination of huge complex subtasks, and each subtask has one neural network that defines the task and is really good at it. So that means we have many, many, many tiny neural networks that are combined with each other, and each aims to exist only for one purpose or one measurement. One is good at identifying cars, one is good at identifying those two wheels, and one is good at identifying trucks. And if the top two are basically saying yes, then it's a car, and if the bottom ones are saying yes, then it's basically a truck. And each neural network has a purpose, has several inputs, and they are differently from each other. So that means, if we look at it as a chart, each of those little squares are a neural network, and if like two say yes, then it's of course a yes. yes and no is maybe, and no, no is no, and no with maybe is no, and yes and maybe is yes. So that means each of those has 4 inputs for each car, or 6 inputs if we have like our truck labeling problem. And given enough data, they can always come up with a solution because they're really good at specialized tasks and don't try to solve everything. The disadvantage of this approach is that we have a shitload of neural networks and a shitload of computation time, like literally, and you can only compute it in some kind of Google Cloud in Sweden or so. And if we use that RNNs, if we use them, the complexity gets millionfold real fast. And I mean that if we have like 1,000 types of cars, then we have like a million times to compute here. And that's really, really not what we want. So, I as an engineer think that this kind of solution with like deep neural networks and stuff like that is a crap technology that doesn't come up with an intelligent solution. And I want to speak to my computer, I want to use it and not to reprogram it. So basically, I, as an engineer, think from an engineering perspective that the old evolutionary idea was really good, but it was not quite there yet because it was not optimized. So the idea behind adaptive neural networks is pretty simple. Adaptive neural networks randomly create connections between neurons. Like all those static neurons that we had before with the grid were totally static, but now those connections are tweaked around and like spawned, and they're like spawned in one point, removed another point, and stuff like that. And by randomization, the idea is by randomization we could always somehow in future perfect solution for the problem. So that means if we have like an adaptive neural network compared with a static neural network, we have like those adaptive new lines that come in between, and they are not the same as these ones, and they're like totally differently connected and stuff like that. And they're basically randomly created and randomly removed. The advantage of the concept of adaptive neural networks is that randomization eventually always wins, as we had before with the evolutionary stuff. And they are always better than RNNs without manual influence. So this is something like unsupervised learning. We don't need to treat the dog anymore because it will figure out the solution itself. Basically, that's the idea. But adaptive neural networks themselves will fail with that concept. But the theory is that in future we have something like unsupervised learning with that is possible. The disadvantages is the crosstalk of neural networks can get worse. So if one neural network is like saying, oh yeah, the color here was blue, the other one says, oh, it was slightly blue, violet or so, then we have a crosstalk because of those randomly connections that could be spawned in, like, directly between each other, and then it will lead for, like, if one was like identifying blue and one neuron was like identifying the violet color, then we will figure out, okay, violet is basically the same as blue, so I can just say violet and blue are the same. And that's the false assumption of false correlations that come with adaptive neural networks. And it means they have a lower efficiency than the evolutionary stuff that we had before because of that crosstalk problem. So then there was a genius guy for my something like I would marry him, but sadly I'm not gay, so I can't do that. But there was a guy in Texas, like around 2004, 2005, that came up with the idea, okay, let's take a step back and figure out how we can optimize our evolutionary algorithm in the sense that it gets more efficient and that it uses less computation time as the crap technology idea back then. That's basically how he started. And he came up with the NEAT concept. And it's the so-called neuroevolution of augmenting topologies, which means we now have something like a composition pattern producing network, which is something like an analyzing system that watches our neural network and figures out how the inputs were related to the outputs. And it's based on genomes, so that means it also has a DNA, and you can reuse it and use cross-species interaction mating and stuff like that. The genetic algorithm is basically the ones that generates adaptive neural network, so that means we have a genome that still produces our adaptive neural network that changes over time, and as the other composition pattern producing network is watching it, we can figure out, okay, that went better over time, so we need to figure out if that specific change in the DNA was getting better over time or worse. And if it's like creating wings for flying, then it's good. So we need to enhance the genome, or the genome part that was specifically growing his wings. Basically, that's the idea. And it still finds the best fitness over the above solutions. So that means we have competing many tiny adaptive neural networks that fight each other and figure out the best solution for the problem. And if one wins, then it gets the mate. And if one loses, then it gets killed. It starts minimally. So that means we have a really tiny neural network at first and predicts maximum efficiency and growth due to the ZPPN. The ZPPN tries to predict how we should start to figure out. It analyzes how inputs were related to outputs, and it figures out, okay, that was the line that was drawing and activating to the final yes answer. So I can use that information to spawn more of those neuron connections more on the path around this yes answer, because it gets more efficient then and has more ways to solve it then. That's basically the whole idea. It's quite more complicated implementation-wise. But basically, as I said before, we have like inputs, like different inputs, and we have a so-called bias. The bias is something like, well, we want randomization always to chime in, because we figure out that randomization is good and healthy for our ecosystem and good for genetics and stuff like that, because otherwise we would have like only white people with blonde hair or so, and we want to have like a randomization part, so we try to have bias in there. And the bias in there is this kind of voodoo machine that is not described here because it's too complicated. But basically what it does is it classifies these different millions or thousands of different neural networks and classifies them as so-called species. So it figures out, okay, these group of adaptive neural networks are really good at identifying cars. So I label them as my car driver species. And this is like really good at like identifying trucks and the other ones around it. So this is like my truck driver species. And as this complex voodoo machine in between knows about those things and how they evolved over time, it can figure out, hey, maybe if I have a truck with 8 wheels, the relations here are basically the same as this one and this one combined. So I can figure out, okay, I try to mate those two and figure out if those get more efficient or not. And that's basically an intelligent mating or mating prediction algorithm or something like that. That's how I would describe it. And that's basically what the guy in Texas invented. So that means the NEAT concept can predict dominant genes, it can predict dominant species in future, and it can predict where to spawn neurons. It respects diversity by gene history markers, so that means every single genome that is generated for each different neural network is classified as a history marker, so you can figure out if like a dinosaur evolved to a truck driver or not, and what were the steps in between, and if like another dinosaur was evolving more efficiently to the truck driver. And if one gets there faster than the other one, they can figure out, okay, this was an unoptimized solution, so we can kill that, and we have a more optimized solution here. That's the idea behind those history markers. It tracks the history, the crossover techniques, and the speciation. Speciation is like the area word for multiple species, just to name it. Those NEAT agents, as it is a competitive system with like multiple agents competing against each other in the evolutionary sense, it has multiple agents, and the best agents make babies based on the fitness, as again in the evolutionary idea. So that means if we have like, for example, Agent Carter and Agent Colson, or Agent Furley and Agent Johnson, we figure out, okay, those neural networks that were randomly created have like new neurons here, and they come up with a better solution in their own species. So that means, okay, we can mate those, and they get to produce babies with their genome from before. The other ones that were not so effective because they lack like connections in there and they don't come up with the yes anyway, so we can just kill them and we don't need them anymore. That's basically what the algorithm does. The advantage of NEAT is that it's basically adaptive to theoretically anything. It figures out anything itself given enough time, because we have the bias and the randomization, and randomization always wins. So if we have like a shitload of thousands of years of time, it will always come up with a solution. And it mutates the connections between neurons. So that means these mutations between neurons, important, are called so-called substrates. Bad wording and stuff like that, we could just use the word connections for them, I will use that, but substrates, just that you understand it, is the connection between two neurons in a hyperdimensional space, but that comes later. And it mutates those nodes or neurons in their locations. So that means it figures out, okay, those different neurons, and if we were like coming up with yes and no or maybe questions or different classifications with different set of outputs, like given more outputs, then we'll figure out, okay, this is something like the optical cortex that is good at recognizing picture stuff, and the other one is like a voice cortex or so that figures out what a voice is. And then we figure out, okay, this kind of adaptation here, or the density in neurons in that specific area is very good at those tasks, and the density of neurons in the other part is bad at the other tasks. So this is what this algorithm also can predict and analyze. And these remarkers are of course awesome. But as we need a shitload of computation time with NEAT, there were some other guys in Florida. Meanwhile, they worked together on that project. And the guys in Florida had the idea, okay, let's try to optimize that a bit further, because we still need a shitload of computation time, and I have a slow computer at home, and I want to use that in real time. So they came up with a solution that's called HyperNeat. HyperNeat because they introduced a so-called hypercube for managing those substrates. So they still have like the CPPN as before. They have still like the evolutionary algorithms that generate the neural network. They describe the patterns of connectivity, that's the so-called encoding, which is also now in the genome, and describe the patterns like symmetry, repetition, or variation substrates, or geometric behaviors. So they figure out if like neurons are connected always like with triangles, then they could be good like at recognizing images or so. That's basically what this algorithm can understand. And it uses a so-called hypercube, and hypercube is a cube that is more than 4 dimensions. Because we have like a big shitload of neurons here, we can't reproduce them in like 2D or 3D anymore. And as every neuron is like randomly created and each new connection in another direction introduces a new dimension, we have basically a hypercube, which is like mind-blowing because we can only understand 3D, so they're basically impossible to draw anymore, and that's why I have no charge. Except for this one. So basically what it does is nothing more than we have still our voodoo machine that recognizes the patterns or species, and it figures out, okay, this one can drive cars, this one can drive cars, but it can also drive trucks, so it can remember those in the genes or the new genome that was introduced, and then it can remember those. And basically what it also does, not only this, does also figure out if the inputs, the 4 inputs, were related to the task or not. So if we have like 4 inputs, and the 4 inputs were only like the temperature or the density of like humidity or something like that, then it figures, oh, okay, those inputs were not related to the outputs, so that means it's not related to my task driving a car at all. So as I mentioned before, it's a hypercube. Minimum is 4D because of the x1, x2, epsilon 1, epsilon 2 dimensions here for the substrates. It can be multidimensional in like 5 or 6D. There are some different implementations there. And the 2D and 3D space inside the hypercube is called the substrate because it's basically the connection then. Anyways, mathematical stuff. So what HyperNeat, as I mentioned before, also predicts is like the relations of the inputs. So it can figure out or classify itself without labeling the data. That this is the front axis, the middle axis, rear axis, right side or left side. So it can figure out if like one of these tires is broken, it could maybe still drive. And if like this tire is broken, it could still maybe drive. But if like 2 tires on one side are broken, then it could maybe not drive, based on how we write our reward function. That's the adaptive idea behind that. So, just to mention it, before in the video there was this generic robot folding a t-shirt and stuff like that. This is implemented in HyperNeat. They're not quite there in RT as HyperNeat, but this is implemented in HyperNeat and it works. And it works real fucking good. Still, it has a problem with computation time. There's some other ideas here. But as we now track basically everything, we are basically fucking Google at home. We need a shitload of necessary pattern data in order to come up with better solutions in future, because we have genes for how the species behave, we have genes for like how the species was working, we have genes how the species evolved, how they were mating, we have the history marker, so another dimension of the genes and stuff like that. So it's basically terabytes of data that we don't want to use. So, but there's still, if we compare the advantages of that, we have still the awesome prediction of geometric relations, so they can figure out like left side, right side, front axis, back axis. We can see if the sensors or inputs are related to each other. we do not require an adaptation of a reward function. We can still use the old reward function, apply it to new tasks. So the goal finding idea is still here, or is here, and compared to other concepts. And it does not exploit the reward function due to the patterns. If it figures out a pattern gets too dominant, then it will figure out, okay, we need to mate it with another one. But mating implies that it gets not too dominant and it doesn't come up with like something like a Captain Obvious solution, like before. But there were some other clever guys. I think they were in Texas and Japan, if I remember correctly. Anyways, those were like, okay, now we have the hypercube, but hypercube is still a shitload of data. How can we solve this stuff? Of course we use, what the fuck did we use? Of course we used genomes for that. And then they figured out a way how to encode everything in genomes that was related to the hypercube. So basically what they did, it's a so-called evolvable substrate hyperneat, or hypercube, whatever. And the idea is that the substrates that we have in hypercube are also marked with genomes, so that we have like genome data that we can evolve to get into a generated artificial neural network on the other side of the whole building in a faster way. So that means it places those connections, or the substrates, automatically, and it figures out a better way to place them. So it figures out, hey, those monkeys there were like recognizing the optical task pretty good, and we now have the task to recognize optical stuff. So give them more bananas or clone them more easily. That's basically what this algorithm now recognizes as well. It respects the neural cloud density. So basically, if we have a shitload of artificial a shitload of adaptive neural network with like millions of neurons, this algorithm will now figure out which kind of cloud density inside the cortex is usable for which specific task. So basically you can imagine it as like sensors in your brain that figure out if you memorize something or if you imagine something on the other side. And this algorithm can now respect the cloud density. And also respects the neural cloud locations, where it figures out, okay, this was the optical cortex or this was the voice cortex. It can increase also the substrates via evolution. So it means as we have like genomes representing our evolvable substrates, we can now use evolution to figure out which kind of new placements of neurons would be better in a future task given the same problem. That's basically what they do. So the advantage of AF hyperneat is that they have exponential growth of neurons via time. The geometry decides where to place those neurons. No. And this was not quite there yet. Then there was another guy, an online guy that put his own files because he can't code so really good, not at GitHub. I think he uploaded it on Dropbox or something like that, a zip file. And he was implementing a new concept where he had the idea to not have an ES hyperneat instance running for like finding out the best solution, but coming up with a probabilistic best solution in time. So that means all those evolution steps that we had before in the evolutionary idea where we were competing them and have different epochs, and after those epochs we made them, now this guy said, okay, now we can basically use that in real time when we limit those epochs to like milliseconds or so, or like seconds. And then we figure out if one performed better or not. So this guy implemented a multi-agent implementation of ES hyperneat, made for real-time usage. That's why it's called RT, of course. It uses limited epochs for the dominance of agents. And the best agents, of course, again, produce babies based on their fitness. So this was the kind of stuff that was already there. There's downloadable code. There's like, what this algorithm is really good at is if you can't describe a problem with an algorithm. So if you can't measure a problem, this algorithm will always figure out a solution. If we have something like a huge maze with like different labyrinths and stuff like that, and we can't figure out our perfect algorithm to go through the whole maze, this algorithm eventually come up with a solution. And it does that real good. So if we have, for example, a racing game, or if we have something like an ego shooter or so, the AIs, meanwhile, behind the scenes are implemented with this algorithm because they have specific tasks, they have specific rewards, like killing each other gives 100 coins or something like that, using this ammo gives 100 coins more or something like that, and then they come up with a solution. But of course, they need to tweak them so bad that they are so bad and dumb that even our stupid monkey humans can still compete with them. But they use those algorithms to implement them in real time. So now I need to drink something shortly because I can't speak anymore. So now we had like the RTES hyperneat idea, but the problem is still that this is like a local offline computer mode thingy. So that means it runs on my computer, or my machine learning rig if I had one or something like that. And the problem there is that all the knowledge that I train there is basically wasted. So basic machine learning problems is if I train a model, I can execute it again on my computer, but if I want to share it with like another one or share our ideas or knowledge that we gained in the training behavior, it's still not synchronized. So basically what the LitJS cartel idea is, I'll show what that means. I found it pretty funny, the naming. So, and but the idea is that we have that in LitJS, as I'm evolving code or as I'm regenerating code that needs to adapt to new problems and new solutions in order to figure how itself worked in the first place. So what the LitJS cartel does, or what my project does, is it tries to write code and analyzes the code given specific problems and solutions that it figures out itself based on the evolutionary ideas of before. So it uses the ES hyperneat pattern, but applies the real-time ES hyperneat idea in a botnet with synchronized bots, each running on hundreds and thousands of agents, each figuring out hundreds of thousands of tasks. So basically it's a shitload of computing problem, but yeah. So the botnet size currently is above like 500K. It's steadily growing. We have like 700,000 like last week and stuff like that because of some deals. But the idea is that we have like a bot or a computer running in our own peer cloud, and each one runs thousands of ES hyperneat instances. But ES hyperneat is really good, but still has the problem of static inputs. So that means we have like our problems. We as humans need to write, okay, that 4 inputs mean 4 tires, and that means I need to write a new function, and a new function should train, yes, you did it correctly, identifying those 4 fucked up tires or something like that. And as a human, I'm lazy and don't want to write code, I basically now wrote an AI that writes its own code in order to figure out what kind of problem it needs to solve in future to get better at that training task, based on the CPPN machine that was, the voodoo machine that was before there. So, why I did that is, I think humans have no clue about inputs. So we don't have clues given a shitload of data, like millions of cars, and we have images of millions of cars. We kind of know why we identify them as cars. But as I said in the introduction, I think we only have like a memory of 7 years, and it's quite limited. And we are unsynchronized because we have voice and stuff like that. So basically 50% of you won't understand a thing what I actually said, but in my head it made sense. In your head it won't make sense because you don't have the same kind of knowledge in order to synchronize our inputs for understanding the same stuff. And I think also that humans have no clue about training data. Even if we think that cars always have 4 wheels, we might be wrong in future. What about flying cars? What about planes? Are planes not cars? Are they not transporting from A to B? These are the kind of problems that this kind of AI tries to solve. And humans have also no time for supervised learning. So I don't have an interface at home, like always saying, yes, that was good, no, that was not good, yes, that was good. 24 hours, I'm like totally asleep and don't want to touch that system again. So basically, I'm not using supervised learning here because I would really get even more mad with that. So in the cartel ES hyperneat, based on this CPPN machine that was introduced before, that remembers the patterns and remembers what the behaviors of different species of the truck driver and cab driver was, and remembers that, this kind of genome now plays also a role for the input. So it means it figures out what kind of training data was genetically relevant to let the species figure out the problem. And it also figures out what kind of training data plays a role, based on the same history markers and based on the same genome ideas. The focus is on performance and cache optimization, which means it runs locally on different bots, and it tries to delegate everything for synchronizations. So I'm not synchronizing like thousands of instances with thousands of instances. I'm only like using the best 10 of them. Currently it's like the best 16 because it's computer stuff. because I'm just using the best 16 of each instance and comparing them with each other if they come up with a better solution. So, what cartel ES hyperneat means is it's a clone adaptive real-time evolvable negation. Evolvable substrate hypercube neat. And that's why I think I found it funny, because now it's unspeakable. It's, as I said, adaptive to varying inputs and adaptive to so-called ligation. Each bot has a so-called Don, which is something like the local leader that decides what to do. And these Dons basically try to synchronize each other with like networking stuff, so they exchange and have an own language and stuff like the language is meanwhile not evolvable, but will be in future. And they hash the inputs and the outputs with a so-called MUMA hash. MUMA hash is like an implementation detail. You don't want to use cryptographic hashes because they need a shitload of computation time. You want to use a hash that is fail-safe and can be used as a hash, but it's not cryptographically safe. So in that case, it was a MUMA hash, because MUMA hash is like the fastest thing that you can do. It's like combined additions and XORs. And the ligation agents clone. Okay, so now that we have like figured out what kind of species can do what more efficiently, we also have like the problem due to randomization that we have multiple agents that may look completely identical. That's what the practice showed. When I analyzed it in practice and figured out that memory dump, oh shit, it looks almost the same like this one, so where the fuck is that? And due to randomization, I now try to optimize it that way that the randomization cannot lead to clones to do the identical thing. So they always have like randomization influencing everything in a better way or in a different way than before. So that means if it didn't come up with a solution or an answer to the problem and it didn't figure it out correctly, then I can now say, okay, this kind of agent or ES hyperneat instance was a complete clone of the other one, so I can completely ignore it because it's not valid to like statistics. It's basically like, I don't know, if you would like go to a church where like all Christians are in, and if you try to ask them, does God exist, everyone will reply yes, but you're asking in the wrong place, because you're asking in a church and everyone in there will say yes. But if you would have asked outside on a marketplace or so, like only 20% would say yes or so. That's the idea, and that we reduce the amount of influence that clones with identical meanings have. And they use those shadow clones in reference to increased fitness, but that's an implementation detail. So basically it looks like this. We have like different bots with each different hyperneat instances with many little tiny adaptive neural networks in them. And then they have a so-called bot conference, which is something like a protocol where they exchange like what kind of leader there was, what was the most efficient one, what had the most ideas of the species, and exchange everything in order to synchronize the idea of the next step or to synchronize the data that they need to get to the next step more efficiently. And that basically means it, as I told, it decides when randomization is good for evolution. The agent clones can be targeted with opposite data sets, so it figures out, hey, you are too good at your task. Now I have a different task for you because I don't want the Captain Obvious here. I want to challenge you if you can still figure out what a truck is. And if it then fails and figures out, no, that's just a bullshitting guy, like some marketing buzzword guy that always tells bullshit, so I can ignore it. And that's basically what this kind of algorithm also tries to achieve. It tries to target all the problems that we had in the past time and tries to re-evaluate if they are still good at those tasks or if they were like forgetting those, even if they're still important. And it has better variance for sigma behavior and better variance for Gaussian behavior and stuff like that. And that has still to be evaluated because I have no fucking clue what kind of time I need for my specific code problem, so that's like the implementation detail there. The academic work still needs to be done because I'm not very good at writing documentation. The reference implementation will be like online around September this year. Currently it's only in the engine and not usable outside the engine, so that's kind of a hard problem, and I try to figure out if it's even possible to exclude it from the engine. It needs some polishing work and stuff like that. Code needs decoupling from the Lucius engine, as I said before. And if anybody wants to write a free doctor or something like that, you can feel free to use so. Yeah, the idea is still to have a reward pattern produce a network, so that means the next iteration step, which is still to be evaluated, or the idea that I have running in my head, is that I want also to figure out what kind of rewards lead to what kind of solutions. because then I would have an AI that I can give a task, like figure out how cars work, and it will completely do it on their own. Because they would figure out what kind of rewards they need in order to figure out what cars are, or they would figure out what kind of rewards they would need in future. But that's basically the idea in my head running. And mathematically, I think there's no chance that I can prove anything of that, because it's always like only code there. Still, I think that the goals are hard to determine, like what the AI should actually do or try to figure out what to do. There's no format of like how to describe a problem. I mean, literally, we have like 30 years of computer science, like in production, where everybody knows about it, and we have like our AI stuff that's literally there for like 40 or 50 years maybe, and no single one was having the idea how to communicate or how to transfer my data from one neural network to another one. And that's basically not existent, and maybe it makes sense to have something like TensorFlow adapters here or so, where other people could reuse the stuff, but this is like, I don't get it from like the engineering perspective, because it's all lost knowledge and stuff like that. The questions that I asked, or the inputs that I asked, they still need to be serializable, so they can be reused and be so that it can generate like training data sets and stuff like that. And for that, I have like no ideas how to achieve that yet, but I'm still working on that. And summary is, everything in there is like, I think there should still be there in the ANN guide repositories, like the talk and stuff like that. The refined implementation for now is the LitJS project, and the LitJS cartel repository is literally zero content, even not a README, because I had no time to write documentation yet. But yeah, that's basically what I'm doing for a living, and I hope I could transfer some of my knowledge to your brains. Yeah, so yeah, that was it. If there are any questions also, I don't know.